All right, shall we start? Okay. Let's proceed with the session number 4, and we'll be discussing network troubleshooting, extending the network troubleshooting fundamentals discussion on the performance degradation and failures. As I mentioned on the last slide, last 3 or 4 slides, it's network failure is not only a complete network down. It can be a partial failure or the performance degradation, which is beyond the service level agreement. And then thereafter, we can discuss on the how to measure the performance in terms of measuring the performance degradation. We need to consider the measuring the performance by using performance metrics. So we will be discussing 6 performance metrics, and one of the performance metrics can be extended up to the level of deep dive because we don't have enough time to discuss deeply on the all 6 performance metrics we are highlighting, but one of them can be discussed in detail. All right, so far we have been covering the introduction, network life cycle, which is on the first session. Then we discussed on the 6 network troubleshooting approaches. Then network troubleshooting fundamentals started with the risk management and network complexity. And then the network failure points, which is control plane, data plane, and management plane discussed in there, and separately software and hardware failures discuss with the options when we need to consider in terms of planning. And now today we will be discussing this performance degradation and failures with the performance metrics involved there. Okay, the network failures and performance degradation. Network failures lead to, these are the couple of definitions. Network failures lead to complete service disruptions, while network performance degradation results in slower speeds and responsiveness. Network complete service disruption, it is quite easy to understand. Network performance degradation results in, so the people are complaining that the network is slow or the application is slow, and we can't wait so long to get the response, and all those things, user complaints comes due to the performance degradation. Network performance degradation refers to the decline in performance or functionality of a communication network over the time. It can be a performance degradation, and certain part of the application functionality can be failed at the time. For an example, application may be having multiple functionalities. One or two functionalities working fine, but some of the functions are not operating as well. So that can be happen if your application providing multiple functionalities by itself, because there can be partial failures. For an example, let's say you have a fiber to home connection to your home from Sri Lanka Telecom, and you are running 3 applications in there: the IPTV, POTV application, and there can be a voice application, which is for the normal telephone calls, and the internet application. Sometimes there can be situations still your fiber is functioning, but your POTV is not functioning, but other two doing well. So those are partial failures, even sharing with the same network link. So those are the functionality fail. The one of the function fail, the application or the function fails, other two doing fine. So that's kind of an example I can give, but there can be situation like in the same application, some parts are working. For an example, POTV, yeah, some of the channels are doing well, which visible. Some of the channels are not some of the channels are lagging. So in the same application, there can be some of the function working fine, some of the functions not doing well. Even channel swapping can be different. Uh, right, let's go to the details. Common network performance issues. Network performance usually can be classified uh, as per classified in this way as well. Let's see, slow data transfer. If you are having file transfer application, you can see that slow data transfer speed is not enough, or throughput is not enough for the application. Inconsistent network performance, that is, sometimes your application is doing well, but sometimes it's not that great, or it's lagging. So its consistency matters, because some of the times of the day it's functioning well, and some of the times its performance is lagging. Can be one of the user complaints. And another complaint can be frequent connectivity issues. Uh, let's say you have a connectivity to a cloud application from your local campus network. So most of the time, you have connectivity issues with the cloud application. That can be a issue at the path between the cloud environment and your local network, local host. So this is usually named as disconnection issues. And there can be issues like if you have a real-time application, such as when you're doing IP voice or the video application, real-time video application, or real-time the conference call. If you are getting remote, these applications are quite affected with jitter. Jitter is, we can discuss jitter as a metric as well. Jitter is a variation of delay, which means the packet transfer times varies between the transfer. Sometimes it's going fast, and the first packet is quite fast, and between the first and second, uh, sometimes average, sometimes getting deviated. So it is not predictable, and most of the real-time applications uh, are affected with this kind of a jitter, which is by definition variation of delay, variation of latency, which it can be affected with the real-time application. If you are deploying real-time applications, you need to measure jitter by using tools. I will be explaining the tools at later of this presentation. Then high latency. High latency is another common issue. If you have applications which is latency sensitive, then you need to plan or design your network based on the latency concerns. There are switches with a low latency, and you need to select your network devices based on this and select the network links accordingly. And the latency matters. Some of the applications like financial, banking, and financial markets, and there are many applications which require modern AI data and AI workloads, and the machine learning workloads usually mattered with latency. And the network congestions. And if you have a network which, let's say you built 5 years back, now your business has scaled a lot with multiple business applications, and business has grown with the same applications with the higher workloads or higher demands, Then if you haven't upgraded or redesigned your network, then there can be network congestions on due to its heavy use. Then packet losses can be there similarly when because if it is overloaded or the malfunction network devices uh, may be a reason behind the packet losses. There can be drops of the packets. Sometimes some applications are quite affected with the packet losses. For an example, if you have a file transfer application, you need to transfer every bit from source to the destination. You can't lose packets, otherwise you need to retransmit. So it is important to reduce the packet losses for certain applications. But some of the applications, packet losses does not matter. Mostly the real-time applications, some percentage can be taken out because it's what matter is sending the messages or the real-time application messages as fast as possible with the minimum jitter. Packet losses are not somewhat compromisable in those scenarios, because it's what really wanted is to transfer your real-time traffic from one end to another end without variating the delay one after another in a sequential manner. And unresponsive or slow applications. Sometimes the network issues are not directly the network issues, because network is enough, but end-to-end application functionality from server to client may be less responsive, but it can be a network issue as well due to workloads or distance. But it can be an application issues as well. When you're troubleshooting, you need to find out whether classify whether this is application issue purely or the system network issue before we troubleshoot. Or you can parallelly troubleshoot as well, but it is good to identify where what's the root cause by your troubleshooting methodology. So this is the summary of network performance issues. Let's go to the details in terms of network performance metrics. We are discussing these few key metrics: bandwidth, latency, throughput, packet loss, jitter, error rate. Unfortunately, we don't have we can't go into a deep dives of all six, but I will select one of these, which is the latency. It is more famous around these days because this AI and machine learning workloads. I will explain how to design an ultra low latency network, or how to manage or troubleshoot low latency network after explaining these six key metrics. Okay, now let's start with the bandwidth, and then latency, throughput, packet loss, jitter, error rate. Bandwidth is the maximum rate at okay, any questions until this point? Okay, let me start there. Bandwidth is the maximum rate at which data can be transferred over network under ideal conditions. This is measured in bits per second. So when you are designing a network or when you are troubleshooting a network, you need to check what's the bandwidth it's built upon. So bandwidth is a kind of a theoretical limit we are using to purchase network devices or design the networks with the components. So usually it's measured by kilobits or the bits per second. It can be kilo, mega, or giga, and sometimes tera as well. So specifically you need to understand bandwidth measured bits by bits, not bytes, because there is something called serialization. when you're working in a machine or computer, it's usually operated by bytes, using bytes. But when you're transferring it to a network, it's converted by using a process called serialization. It's a conversion from bytes to bits. So in this case, we are measuring the bandwidth by using bits. So the one zeros after one by one. So usually that's the measure. So if somebody asks what's the measurement of bandwidth, it's a bits per second, right? So bandwidth is important when at the point of you are designing the network. Let's say you are starting a company and now you wanted to have greenfield, very brand new network in your campus environment or your building environment. So you decided initially with the average bandwidth of 1 Gbps, 1 gigabits per second, a network build initially, and after let's say your business has grown within last 3 years tremendously, and you identified that your network 1 Gbps network is not enough for your entire communication because there is a high demand for the bandwidth or so you can upgrade it to 10 gigabits as the next step. So there are multiple gigabits per second developed over the years. Initially, I can remember my first career days. Usually, we had networks with the local area networks with 100 megabits per second, and some of them, the predecessors, have been experiencing 1 megabits per second, and then it's evolved to 100 megabits per second for the LAN areas, and then later upgraded to 1 gigabits per second. And nowadays we are having 10 gigabits a second copper wired on most of the area, most of the new buildings. And it is data centers mostly coming with 10 gigabits per second, which require higher bandwidth for the server connectivity. And data center networks are now with mostly average, the new developments are not 10 gig, mostly at least people going for the 25 gig per second. And there are where the IEEE standard variants of standards for 50 gigabits per second, 100 gigabits per second, and 200, 400, and as well as recently I noticed NVIDIA published 800 gigabits per second network cards or smart NICs, and there are switches for the 800 gigs. And most probably end of the year, we can see the 1.6, which is the double of 800 gigabits per second network devices and smart NICs as well for the AI workloads. All right, it's matter mainly on the data flow. So let's go to the latency. Latency is the time taken by time taken by a data packet to travel from its resource to the destination in a given network. It is measured in seconds. So latency measurement is usually measured by time. So it is important to get understanding on the metric as well as the measuring units. The previously bandwidth bytes per second, and between the source and destination. If you are connecting, let's say source can be server, destination can be a client or vice versa. The source computer to destination computer must be having multiple networks or network links and devices. Still, end-to-end bandwidth can be measured. For an example, there can be let's say you have a source server connected to 10 gigabits per second. Your destination or client machine can be 1 gigabits per second, because server required to provide the services to multiple clients. So you need to have higher bandwidth at the server end, rather, but you can have lower bandwidth at the client end, because server require to connect with server, provide band data to send data to multiple clients, and it require higher bandwidth. So you don't need to match the bandwidth between the two, but there are situations you need to match as well. But most of the time, server client architecture require server to have higher bandwidth and receiver to have a lower bandwidth. So, uh, then go back to the latency. Latency measured by time, as a time. The previously bits by bandwidth is bits per second. The latency measured by time. But computer times are usually not measured just by seconds, because seconds, if you see seconds on your packet captures, it means your network is not impacted with the latency hit. So it's usually measured with the started from milliseconds, then microseconds, nanoseconds. Nowadays, we have picoseconds as well. The millisecond is 1,000 of a second, and microsecond likewise. Millisecond is 10 to the power -3, and microsecond is 10 to the power -6. Nanosecond is 10 to the power -9. Picosecond is 10 to the power -12. So in low latency network, usually we expect traffic flows to measured in microseconds. So nanoseconds usually implement. We have another lesson at a later of this course with the time synchronization and time stamping. So we will be discussing details in terms of monitoring there. So nanoseconds usually involved in the time stamping and time monitoring for the precise networks, so the low latency network. But most of the enterprise level applications, the flows are measured in milliseconds most of the time, and microseconds at the low latency space. And ultra low latency space, we are considering nanoseconds. Now it's possible to measure the picoseconds as well with the modern network monitoring devices. Right. Factors affecting latency are physical distance. The latency, we will be discussing this in detail, because I told you that one of the metric I will be taking separately and explaining you the details for the deep dive. The physical distance, because let's say the Colombo University and Peradeniya University has a link between for the intercommunication between universities. Then the physical distance matter, because within the Colombo University, different department between the Colombo University itself, which is on the same local area network, latency may be lower, but higher latency when you are going through the interconnected network through a wide area network. So physical distance matter, because speed of light mattered here. Electromagnetic signals maximum speed in the world equivalent to speed of light. So physical distance matter, because light has a maximum speed. Then the factors affecting other factors affecting network hops. If you have multiple network devices between the source and destination, other than the cables, so it matters as well, because devices have some certain processing time for the data planes. And network congestions. If there are congestions within the network due to bandwidth constraint or throughput constraint, then there can be drops, congestions, or the rescheduling of packets or delaying of packets are possible. So if there are network congestions, then it is increasing the latency. The transmission medium. So you have basically transmission mediums such as copper wires, and optical wires, fiber optics, and then you can have wireless communication. So all three media have different latencies. Usually you can measure usual acceptance is fiber has the lowest latency and copper is a bit more higher. And there are the Wi-Fi usually highest latency in terms of latency perspective, but there are situations you can see that Wi-Fi or the wireless have a lower latency due to a physical distance. For an example, one of my London clients, they said within the London, the fiber communication distance, fiber wire has a longer distance, and the line of sight having the line of sight with the Wi-Fi wireless signaling, it's faster. So it's depend on the situation, but media matters because transmission media, the light speed changes with the medium you are using to transfer the electromagnetic signals. So these are the factors affecting the latency and the mitigation strategies or reducing the latency reduction strategies are optimizing the routing path, shortest path. If you can find a shortest path based on routing technologies, so it is quite possible to reduce the latency rather than taking a longer path, get the shortest path algorithms running as dynamic routing protocols on a network devices. Using content-defined distribution network. You can use strategies such as content distribution network technologies, which are higher bandwidth, lower latency, and there are several ways to traffic engineer with this CDN. And edge computing is quite possible because if you are processing your application client and the servers within the same VLAN, you get the same local area network, then you get the lower latency and the applications. But some of the cloud hosted applications, we need to go through the multiple networks, local area, cloud net, intermediate service provider networks, and then to the cloud network. So your application latency may impacted due to the distance and the number of network hops and transmission medians and all those things getting involved with the where you hosted. So edge computing using as a strategy to reduce to make your application clients and servers are nearby. So this is quite important. If you have a if you have a remote application, then obviously your latency is high. That's why edge computing is useful to reduce the latency. So you can upgrade your hardware infrastructure, because if you have a hardware infrastructure which is more than 5 or 10 years, which is obsolete or end of life, now not supporting or not, those devices are not considered in terms of latency workload at the time of your deployment. You can select new devices based on the latency demand or perspective, with low latency switches and the cables and low latency network equipment, and the servers can be tuned for the low latency, and all those things can be done. So upgrading your hardware and some of the software can be used as well. Acceleration techniques can be used as well. Those are the latency reduction strategies. Okay, we discussed on the bandwidth, latency, and then now on throughput. Throughput is another metric. Throughput is the actual rate which data can be successfully transferred across the network. Even though we consider bandwidth as a starting or as the maximum rate, usually after the deployment, you can see that it's not running its 100% capacity. Even it is 10 gigabit per second, If you try to load it, it is difficult to sometimes load due to different factors. Uh, 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 Considering the TCP/IP protocol, protocol laggings, and all those other components may not allow you to use 100% for all your applications. So there is always cap to achieve the maximum numbers. There are possibilities to further tuning, but usually you can measure the actual bandwidth against the theoretical bandwidth. Theoretical bandwidth, it is quite important when you are designing the network. But when you are maintaining and running the network, actual throughput is the metric that matter, not the bandwidth. Because even though you have the enough sufficient bandwidth, the design, your application servers and the applications not functioning up to the level of this due to various bottlenecks or the loading conditions. So you need to measure your actual you can measure your actual throughput when you are troubleshooting. When compared to the bandwidth, which is the theoretical limit at which data can be transferred, which may or not be achieved. So you can't expect always you can hit the 10 gigabits per second even if you have 10 gig. So that's why you need to measure the throughput, actual throughput, which is lesser than the maximum bandwidth. Throughput is the real world data transmission capability that can be achieved, and it is measured in bits per second. Example, similarly, when you are measuring bandwidth, it's kilobytes per second, the bytes per second. Similarly, throughput measured in the same way. The theoretical limit of the bandwidth can be affected on these scenarios: network congestions, hardware limitations, because let's say even though you have 10 gig, your hardware, your switch has hardware limitation, or you have multiple network devices between source and destination. One of the switch have a limitation which you can't achieve the maximum limit, even though it's physically 10 gigabit or maximum defined as 10 gigabit, supported maximum of 800 Gbps or 800 Mbps. So it can be happen. It's based on you need to check the device. It's the maximum possible throughput by measuring it. And there can be protocol overhead, because when several networks run on several control plane protocol and data plane protocols are sometimes overhead itself as well. For an example, TCP/IP is not it's designed the standard published more than 50 years back. At that time, there were no concerns on terms of low latency based designs. So TCP/IP is by natively not considered as low latency protocol. There are several other alternatives or improvements in terms of improvements possible to increase the throughput, and there are operating system settings, throughput oriented tunings. And interference, there can be interferences if you are using copper cables, quite possible having interferences, so it can be affecting the theoretical maximum bandwidth to have lower throughput compared to the maximum level. In fact, to reduce the throughput, you need to use the tuning of the actual increasing the actual data rate. So these are the first three. Any questions until this point before we go to the next metric? Okay, let's move to the packet loss. The packet loss is quite understandable, but packet loss is how to measure is packet loss is the percentage of data packets that are sent from source but never reach at the destination and are lost forever. So there is something called quality of service. You can delay by implementing certain quality of service methods. You can delay the packets. but packet loss is not considering delays. It's considered entire losses. It will, if source has forwarded certain traffic targeting a destination, but some of the packets lost between the between the source and destination. But it's not delayed, it's just lost forever. So those percentage of packets lost is one of the metrics to measure a reliable network. So data packets transmitted and received are measured against each other. So that can be done by using different tools. So some of the causes or contributions to packet losses are network congestions, faulty hardware in between, network hardware, signal interference. As I said, on the copper cable, software issues can be there in terms of certain software malfunction. Software may be dropping client or server or intermediary network device. So it make a result of degraded network quality. Then one of the measurement of network quality is this packet loss within the network, lag and network issues. So it may lag your applications because some of the applications are not resilient to packet losses. By resending TCP/IP, mostly TCP stack, TCP protocol, which is three-way handshaking protocol, is quite capable of handling losses. But there are situations it is not efficient to run your application, so you need to build your application considering the packet losses as well. If it is not reliable, usually the developers are not considering assuming that the network is fair and running well without packet losses. So that's a correction is from the network engineer or network ops team need to take the responsibility. It's affecting mostly the real-time applications, which is real-time voice or video applications, affecting if there are packet losses. So it is difficult to run the real-time applications. Okay. Then finally on there is another metric, which is the fifth one. It's called jitter. Jitter is called the defined as variation of delay. So it's something like this. Delay is fine if you have a predictable delay, that is fine. But if you have a variable delay, which is most of the real-time applications unable to cope with it, because applications are usually built with assuming the predictable delays. But your network delay is varying with the time, so it is difficult some of the applications to run, usually the real-time applications, because first packet reaching on a, let's say 100 millisecond, then the second packet reaching after 500 milliseconds, then it is affecting heavily for the applications. So the difference between delay between different packets within a flow, packet flow, is quite useful to measure when we are troubleshooting related to real-time application. There are tools like iPerf. This is open source tool. Anybody can download. Windows and Linux are there. This is an example output to measure the iPerf by using iPerf. So you just need to give source and destination, then run the iPerf application as a server and client. So the output defining sending packet, this is by slots of 1 second, and first second it has sent 112 megabytes, and this is showing the bandwidth, which should be the throughput, I guess, right? Because actual bandwidth on this flow, it's 939 megabits per second. And you can see it clearly. The transferred initially 112 megabytes. The bandwidth or the throughput measured here is 939 megabits per second after the serialization. And then it's measured the jitter, and the right side showing that packet losses, percentage of packet losses. On this 112 megabytes transferred within first second, uh, having 414,373 packets transferred and 39 lost. Loss percentage is 0.27%. And it's transferred with a speed of or the throughput of 939 megabits per second. So this is the output. This is quite useful to measure, to baseline your network before deploying your applications. Or if you have application issues, rather than troubleshooting just by the applications, you can check with independent of the application for your network performance test by using these tools to benchmark or the baseline the network to check the readiness or troubleshoot the network. So it's kind of a tool quite useful to measure, understand the jitter, variation of delay. Usually this is a kind of a better network, because I assume that less than 1 millisecond of jitter is fine for networks, but there are still packet losses. So that's a concern, that may be a concern for based on application requirements. So it is quite useful tool. Probably we can, I will check with the course coordination team for a practical session with an instructor. So probably we can run these tools and get understanding on the various scenarios there. Let me check and come back to you on that. So I'll be sharing these slides. Probably you can install IPERF on your machines and test variations if you're interested. And that's about jitter. The final metric I selected is somewhat physical layer, which is the error rate measurements. These are possible to measure on various ways by cable testers and all those things. The error rate measures the frequency of error that are occurring in the data packets that are transmitted over network. Error rate usually can be measured on several layers, but in this case, the most of these are physical layer checks. It's what is the definition is network error rate percentage is number of erroneous packet divided by total number of packet transmitted, and make it percentage. It's quite simple for the equation, but error rate is also called as bit error rate. It indicates the number of bits that have been altered due to noise, interference, distortion, or synchronization errors. When you are sending, usually, I think telecom providers, if we complain that our network, the WAN link is, the ISP connected link is not functioning well, they come and do the bring out the testers and all those things and run something called BERT test. So they measure the error rate initially if there is a physical issue on the link. Similarly, we can do use the cable tester to test between source and destination if there is a suspect on that. So this is there are some other ways as well, especially on the network devices. When you are checking errors, there are few error detection techniques. Usually, what I do is when I troubleshoot switches or the router physical ports, or sometimes network cards, we can check cyclic redundancy checks, CRC checks. And there can be, maybe since you are cybersecurity experts, we can use checksum as well. There are other error detection techniques like virtual vertical redundancy check and longitudinal redundancy check as well. These are for your note in terms of error detection techniques are there to measure the error rate of your physical links in terms of correction testing. Sometimes quite important because there can be it is mostly identified issue on the local area network is this physical layer issues, cabling issues, when your network is somewhat old but traditional, but if it is because uh, uh, if we troubleshoot on upper layers, but we couldn't understand the dynamics below at the physical layer, it is somewhat lagging in terms of understanding troubleshooting by the holistic view. So it is required to measure your physical layer errors as well. So error rate is an important metric in terms of overall troubleshooting if you have a suspect on the network in terms of troubleshooting segments. Okay, those are the 6 metrics which I wanted to introduce. There are several more metrics as well, but in terms of the day-to-day work and troubleshooting stuff, these 6 metrics are quite useful on your network troubleshooting processes, at least for the start. Okay, let's move to the, are there any questions before I move to the few troubleshooting tools? Okay, the most simple and basic everybody knows this and troubleshooting tool is ping. We have been discussing this on troubleshooting approaches as well. If you do a simple ping before you complain or open a trouble ticket to network or systems engineering team, it is quite useful information for them to start decide the troubleshooting approach, whether it is top down or bottom up or divide and conquer. You can, if they have more information like ping output, that can be quite useful in terms of ops person to troubleshooting engineer to help you out. The ping is a standard latency test tool available on all the operating systems. It measures the round trip time between your PC and the target, your specified domain name or IP address. The round trip time is the time taken for ping packet, which is ping belongs to ping is an application, and it's built on top of the TCP/IP stack protocol named ICMP. So ICMP, when we are discussing details on the TCP/IP model, probably we can discuss details on the where ICMP putting and which layer and all those things. So ICMP is a layer protocol. The part of it protocol is at layer 3, and you see that layer 3 and 4, I guess, for the entire ping application. You are sending ICMP message from server to from your source to destination, and returning it back to the source or reflecting it back to the source is the function of ping. You don't need to run the application on the source and destination both, because ping response is quite natural. You just need to run from your source machine only. There are some tools you need to run both source and destination as well. In this case, most of the applications supporting the ping application, responding response also reflection also from the remote machines mostly enabled, because it's natively support ping or ICMP reflection. So it measures the total latency to get the response. You are measuring the up and down latency. It's marked here with the milliseconds, 20 milli in this example. Somebody ping sent to one of the URL, one of the websites, and it has returned with 20 millisecond latency at the first response. Second is 24, third is 20, and calculated the average below. Minimum latency is 20 from the all four outputs, and the maximum is 24, and the average is 25, which means added all four latencies and divided by 4. And no packet losses as well. If there is a packet loss, it will not, it will be shown here. And 4 packets sent and receive 4 packets received. This is a simple map application on all the computers are supporting, which is using the protocol named ICMP. Measure the round trip time as the main output. Okay, we discussed this on one of the troubleshooting approaches as well. Traceroute is another application. The ping is quite useful to measure the latency and reachability to a remote host. But it has its own disadvantages. Sometimes due to the security concerns, ping protocol, ICMP protocol blocked for certain servers and the network equipments, which may not be useful sometimes. I can tell you, and the alternative tool for that, there is something after this traceroute explanation. So traceroute is another tool which is available on the Linux, Windows, and all the operating systems. It is measuring the time to live. It is using the time to live field of the TCP IP stack to measure the latency between various hosts between source and the destination. As in this example, the source computer and the destination computer connected by using intermediate 3 network devices. So these 3 network devices are layer 3 devices, which mean routing function enabled. When you run this TTL traceroute application, what does it doing is it's sending a message ICMP echo request with TTL number 1. Then it expires at the first layer 3 interface of which is a router in this case, and returning back to the source. Then you are sending the second packet with the TTL2. It's reaching the up to the second network device and responding back, expiring the TTL timer at the second device. Likewise, on the third, you can send, it will automatically send the packet with a TTL3 and getting a response from the third one. So incrementally adding 1 to the TTL field by each workflow, then you are getting until up to the last destination, you can get number of hosts by running this application. In this case, you need to send 4 times to understand between server sender and the receiver. So you know that these are the devices responded, which is in between source and destination. When you are troubleshooting a network path, this is the application which is quite useful, and it's again similar to ping, running by using ICMP protocol. So ICMP is quite useful control plane protocol, and it is mostly useful in terms of ICMP enabled environment. Some of the devices disable it, as I mentioned, on the security reasons. And this is an example of output. You can see that traceroute output. In Windows, we are when you run it, the command is trace RT, but for the Linux traceroute is there. So you can see that three values. On the second router responded with the three latency values, which is measured up host, minimum, maximum, and average. Average and maximum. Those are the numbers provided in terms of the variation. And you can see that number 11, ICMP, this particular network device at the 11th host is filtered with ICMP, and which means ICMP security implemented to block the ICMP. So you are not getting response from that particular device to because it's implemented to block the ICMP protocol, and it is not useful in the such scenarios. But it will progress to the next stop, and if your endost is responding, then at least you can get the number of hosts in between. But and passing that, you can understand that traffic is passing the devices, but just not responding ICMP in between devices. So that is a drawback. If ICMP disabled on certain areas, you can't get the exact picture of your host between source and destination. There is something called my trace route, MTR. So you can use that MTR tool to, if one of your applications working between source and destination, and you are in application to work, you have enabled one of the TCP ports. You can use that custom TCP port to check the reachability, connectivity by using the my trace route tool. Let me add, I will add my trace route output to the appendix. Maybe it's useful tool when the ICMP is disabled and not you are unable to trace down the intermediate host sometimes. So we discussed on the ping application, then trace route. Then there are other two troubleshooting applications which are quite useful and standardized, but mostly these are implemented on the network devices, and these tools are industry standards. One tool is OWAMP, which means one-way active measurement protocol. This is defined by request for common standard, which is 4656. And quite ratified standard by IEEE, and this standard tool, which is quite useful for one-way delay. If you want to measure, if you are doing measuring the two-way delay, you can use the ping tool. It's providing ping pong latency. If you really want to measure the one-way latency, which is for usually there are applications which is running only one way, which is there may be situations, the forwarding way, transmission direction, and the transmission path, and response path, return path has a asymmetry based on the modern day routing, because there is something called asymmetric routing. The sending path and receiving paths are quite different. So in that case, if you measure the ping pong latency, it's a kind of average between transmission path and receive path. So you can't get the correct figure on the one way. Application sometimes running other than TCP, UDP is running source to destination only. There is no response in between. So usually for those cases, if you need to measure the transmission latency for one way, you can use this tool on considering all those applications. For an example, let's say Gold Road, the Gold Road from, I think, from Savoy to the Vellavatta to Kolpiti, you can see that there is an asymmetric path. Gold Road, the general traditional Gold Road, and duplication road is the reverse path. Sometimes you don't get within the network, you don't get the symmetric path. Sometimes there can be asymmetric path in the IT networks as well, based on the routing, asymmetric routing configurations. So similarly, if you need to check on the one-way latency between a source and destination, can use this tool, but you need to run the application on the both side. That's a disadvantage. For ping and trace route, you don't need to run on the source and destination, but in this case, you need to run the application on the sender side as receiver side. So there is if you want to measure the two-way uh, uh, two-way active two-way latency uh, by using similar by running the application same application on both the side. It is possible with TWAMP protocol or tool as well. Two-way active measurement protocol is the name. The previous one is one-way active measurement protocol. These are standard tools defined by RFCs, which is request for comments and standardization process by IEEE. So this is quite famous tool, the famous tool some time back, and it's quite available on the network devices. And initially, the control between client and server built by TCP protocol. Then it's the latency, two-way latency measured by UDP. There are certain applications we need to use this tool to do a baseline test or use application readiness test. So quite useful in terms of getting better the exact numbers in terms of measuring the application, both the server and the client. These are some of the examples I put up on the implementation or on the network devices to measure the two-way latency between, if you want to measure the two-way latency between two routers, two network devices, it is quite possible to run on the router control plane by using as similar to this example. All right, these are the tools I just wanted to introduce today in terms of as initial discussions. We are going deeper at a later of the course with specific, we have something called the analysis sections. We are using Wireshark and going for the deep dive of packet analysis, and we can go for the deep dives on those lectures. But for the initial troubleshooting purpose, these are the standardized tools and mostly commonly available in terms of measuring the metrics, what I mentioned before. And mostly in terms of latency measurements, these tools are quite useful. All right, do you have any questions until we go to the deep dives on the latency as a selecting latency as a matrix, and then we are discussing how to reduce the latency by our designs and improve the performance or metrics considering the latency as the metric there. Okay. Okay, these are somewhat new in terms of mostly because the latency became a serious issue with the latest workloads such as AI, machine learning, and the modern core banking and banking applications, as well as financial markets. And there are several applications now. Latency is a concern, and low latency and ultra low latency networks are quite important in some for those workloads, and reducing the latency, especially in terms of these gaming applications. Sometimes for the home networks are important because there are many number of gamers now. So considering home networks as well as enterprise and data center workloads, we can consider discussing detail in terms of latency as a metric. Other metrics we can we will not able to cover deep dives in terms of time constraints, but latency we can go into details, and you can learn from this and apply to other metrics as well for the deep dives. So as I initially mentioned on the last week, we are not limiting the scope of this course to the physical network device scope, but we are extending it to host networking as well, which is on the servers and clients endorsed networking. So in this case, I just put up a diagram which is as an example on the latency of each component. So applications usually having variable latency based on the application development process. Different applications have different latencies. Some of the applications require ultra low latency. So development team taking care of building the application based on the design patterns and the software technologies, which is having the lowest latency. It's a different thing. It's beyond our scope of this course. Latency optimization of applications are quite possible by application teams, and it may be a scope of another course. So, but there onwards, other latencies we can discuss. The networking stack of the operating system. For an example, kernel TCP/IP stack, the operating system usually getting involved there with an example of 10 microseconds of latency. It's taking 10 microseconds to kernel to process TCP/IP packet. And then there can be a network driver and the network card and serialization from converting from bytes to bits. It's taking another 10 microseconds. And then after sending through the network card to the first switch, which is the access switch or the leaf switch, it's the switch port to port latency can be 3 microseconds usually for enterprise grade network switch. So then thereafter it should be sent to the top of the this can be a top of the rack switch, which means data centers can be or racks can be have switch for each rack to connect the servers. Then there is a end of the rack switch, which is can be spine switch or core switch for the aggregation of switches. Then it's the intermediate core switch or the spine switch taking 7 microseconds, and then there is another switch which is connected to the server application, and it is again top of the rack switch. It is similar to that the client side 3 microseconds, and these are rough numbers just for your example. And then again server side network card take and serialization process taking 10 microseconds, and network stack taking another 10 kernel TCP/IP stack taking 10 microseconds. You can see that usually the ping pong latency between round trip latency between network latency is somewhere around more than 30 microseconds if you added up. So this is just for an example. If you want to reduce the latency, you need to reduce all these separate components to reduce the end-to-end latency. It is not sufficient to reduce the switch latency or the kernel latency or the TCP/IP latency or the network card latency. You need to reduce all the latencies if you want to reduce the latency. That's where we started with this. I want to start with this particular diagram. So let's see how we can do. We need to understand the component of network latency as a separate segment. Okay. Any questions on this particular slide? If you are if you don't agree with our perspective. Okay, let me define uh, the network latency by different delay components. Distance delay. Previously, I discussed the physical distance matter in terms of latency because there is a limitation of speed of light. And different mediums even matter. For an example, optical cable sends bits at 5.5 microseconds per seconds per kilometer. It's taking the optical cable uh, bit transfer by using optical cable takes 5.5 microseconds per kilometer. So which means number of kilometers getting increased, uh, which means your distance getting increased, and between source and destination, then your latency will be higher. And some copper cable is bit slower and it's taking more time than the fiber optic cable, slightly higher in terms of transmission speed, and it take 5.6 microseconds to go travel 1 kilometer. The satellites are the worst because it's taking more time through the air, medium matter. Uh, no, it's send faster, but there is a problem in with the distance because satellites are on the sky and you need to travel long distance. Even if you are transferring traffic, it need to travel up to the level of satellites. Now I think Starlink started lower altitude or the closer satellites than the traditional satellites network, and the latency is much lower than the traditional satellites by using a Starlink network, but still higher compared to fiber and uh, other ISP technologies used in Sri Lanka, I guess. So, but still, it can be a better alternative for the rural areas because you have a better coverage other than otherwise you need to lay the fiber or copper network around the land through the by the land. So anyway, I just wanted to highlight the fact that the main thing is distance matter in terms of the latency, physical distance from Colombo to Peradeniya or Colombo to Kandy. Latency is higher, low latency is higher than Colombo to Nugegola. I think that is difficult to optimize. If you are communicating between Colombo and Kandy, it is difficult to reduce because it's by nature it's limited by speed of light. So that's difficult to optimize. But there are research going on this quantum physics. There is something called quantum entanglement, which is which is uh, somewhat tested in terms of possibility to do a instant communication faster than light speed, but those are still not practical in terms of real world deployments. But generally, we can assume that it is difficult to optimize distance delay due to its physical distance between locations of communication. And serialization delay is the second component. The serialization delay, I previously mentioned that by using network cards of your machines, either Wi-Fi or the copper network or fiber network connected network cards of the servers and computers. Usually within the computer, it's operate by using bytes. The network card is the one converting bytes to bits. So usually byte has 8 bits, and this conversion process take time. So usually, if there is a point to it is possible to reduce the latency by using uh, bandwidth, which means usually by increasing the bandwidth, we assume that it is possible to transfer more data by increasing the bandwidth. But there is another advantage as well, because it is possible to reduce the serialization by delay by increasing the bandwidth. That is another side effect of increasing the bandwidth. So for the low latency network, maybe you have noticed they are using large pipes, which is 10 gig, 25 gig, 100 gig for the data centers. It is not just the purpose of it require large bandwidth, but sometimes it's for the latency, because if you have a large pipe, it's quite possible to communicate parallelly. You can send multiple packets parallelly with the serialization process. So basically network card sending with the bytes and you are converting it to bit streams. Can send parallel bit streams within this serialization delay process if you have a large bandwidth. So you can optimize the serialization delay by increasing the bandwidth of your networks, data center or campus networks. That's one of the ways to reduce the latency. So distance delay, I told you that it is difficult to optimize. It's it's limited by speed of speed of light and distance of the source and destination. But serialization delay can be reduced by increasing the bandwidth. We'll show you for an example. If you have a 1 gigabit Ethernet, serialization delay will be 12 microseconds. But if you increase your bandwidth of the machine, it can be it's taking only 1.2, 1/10 of 1G due to the parallelization. Can get 1.2 microsecond from 12 to 1.2 is more than 10 microsecond reduction. It's a huge reduction. So that's the reason some of the data center low latency data center providers are using higher bandwidth pipes. It's not the reason of they are using entire bandwidth pipe, but for the purpose of reducing the serialization delay. Then the third delay included in the total overall network delay is the amount of time packet must spend in a buffer waiting its turn to be transmitted. There are situations the buffers to handle the reduce the packet drops and when there are peak situations. So these buffers introduced on to manage the flow and flow controlling. So sometimes we implement something called quality of service to prioritize the traffic. Those technologies and these buffers taking time, adding the latency, and that's called usually queue delay. That is, you can reduce the buffer size, optimize the buffer sizes to minimize the latency when you are tuning the latency, end-to-end latency. Then the forwarding delay. The forwarding delay, amount of time it takes network device to. In the previous exam, these network devices taking few microseconds. The first one, the blade switch taking 3 microseconds, core switch taking 7 microseconds. Actually, these switches, even though the data plane and control planes are taking time to forward the traffic, that's usually called forward delay. So these network devices have two ways of forwarding. They have something called stow and forward and cut through switching. We can discuss that in another slide. By using the forwarding methodology on the switches, so the network devices, we can reduce the latency. For an example, traditionally we were having enterprise network switches running with the stow and forward. These are cheap switches. And the modern data centers which require low latency implementation actually run on cut through traffic, because almost immediately passing the traffic from source port to destination port by reading the first few bytes, first few uh, um, uh, first few bits. So you don't need to get entire frame within to into a switch to pass it. But store and forward, it's take time. It's waiting until entire frame to be in the switch buffers. So if you need ultra low latency, you need to purchase a cut through switch rather than getting a store and forward. So that's the minimization option of forwarding delay. The protocol delay. Protocol delay is, as I mentioned before, the TCP/IP stack developed more than 50 years back. There were no latency concerns or considerations at the time. So later, these protocols definitely have an have an overhead. So it is matter if you optimize the TCP/IP or using the alternative modern day latency optimizable protocols. So selecting the protocol can be useful in terms of ultra low latency environments with modern developments. So these are the 5 major components I can tell you which we can consider optimizing. So this considered overall network latency as subcomponents in introducing the latency. Any questions until this point? Okay, let's go to discuss the details on the serialization delay. Serialization delay, it's a kind of I just wanted to share this particular slide in terms of comparing the different bandwidth. I told you by increasing the bandwidth, serialization can be reduced due to the parallelization and the physical layer. For an example, you can see the physical layer bandwidth and the data link layer bandwidth and the encoding methods displayed on this. Ethernet 10, I told you initially when I start the career, I started with Ethernet 10 Mbps standard, and its physical layer bandwidth defined by the standard is 10 megabits per second. The encoding is when you are usually usually for the data, it's having 8 bits, but additional 2 overhead bits when you are converting bytes to bits. So 2 overhead bits are there. So it means almost 20% overhead is there for the 10 gigabit by the physical layer to data link layer conversion. Data link layer usually, so due to this overhead, the realistic bandwidth of the data link layer, which is bit from the MAC layer, the data link layer is the second layer, physical layer is the first layer of OSI. Due to this encapsulation and the overhead encoding overhead of the encoding methods, effective bandwidth at the data link layer is 88 Mbps, even though it's optimized for the standard defined 10 Mbps, can get maximum of 10 Mbps due to this overhead. All right. In terms of the 100 Mbps, you can see that the similar encoding method still getting 80% of effective bandwidth for the data link. Gigabit, there is an optimization because standard define rather than defining the bandwidth at the physical layer, the new standard on gigabit, they defined the standardization authority, design the protocol 1 gigabit per second gigabit Ethernet protocol with the data link bandwidth of 1000 Mbps. Physical layer is 1250. By using additional voiding same encoding method, you can get the effective bandwidth of 1000 Mbps. And new encoding method, because the overhead of the traditional encoding method is high, then they introduce new encoding method, which is 64-bit effective and 2 additional bits taken as an overhead. So in this case, the effective bandwidth still on the data link layer kept as 10,000 and 10 Gbps standard defined. Then again, similar encoding method follows on the 40 gig as well as 100 gig. Now we have 25 gig as well. So you can see an idea in terms of where the details deep dive in terms of selecting the particular bandwidth and the effective bandwidth in terms of comparing the physical layer and the data link layer. These are tiny information maybe you need when you are planning for the network and measuring the bandwidth. Okay, this is one reason. Let's say even though physical layer, you assume that your 100 Mbps network should get the throughput of 100 Mbps. It's by default based on the standard you can't get 80. The throughput is maximum you can get is 80. So bandwidth doesn't define there is a difference between bandwidth and throughput. You can understand it by this slide as well. Is by theoretically different layers defining different bandwidth sizes based on the standardization. And this is the diagram I can show you in terms of explaining the serialization delay. So 10 Mbps bandwidth with the frame size, the layer 2 packet size. Minimum frame size usually 72. The maximum MTU, maximum transfer unit defined for your networks are usually 1500. So minimum smallest packet size can be sent by 84 microseconds. And the maximum frame size, which is 1500 bytes, can be sent by 662 microseconds. It's 1500 serialization or 1512 microseconds. So you can see then when you upgrade it to 100 Mbps, your latency is reduced by 10 times. It's 8.4. It's a tremendous difference, reduction of latency. Similarly, if you go for 1 gigabit per second, your serialization delay reduced less than 1 microsecond. And 10, if you go for the 10 gigabit, it's less than 100 microseconds, 100 milliseconds. So likewise, you can see that reduction of serialization delay impacted by the bandwidth increase due to the parallelization. So it is important to understand that not increasing the bandwidth, not giving you the more room and space for the applications, but reducing the latency as well for the latency critical applications. And for the jumbo frames, which is more than 9,000 bytes, these are the numbers. Some of the data center applications modern day using jumbo frames. I previously mentioned you the smallest size and the maximum MTU frame size 1500, and now the jumbo frames. So if you got the idea that latency optimization possible with the increase of bandwidth, so that is quite important as a network designer or network troubleshooter or the such a person who advising to increase the performance of your network. So this is quite important to understand. Then let's discuss about what are the network Ethernet standards available in the world. Now, the previously 1980s we have been using 10 Mbps, and 1990s we got 100 Mbps, and then close to Closer to 2000, we got 1 gigabit Ethernet standard. Then around 2002 and 2003, I guess we got 10 gigabit Ethernet. Mostly these 10 gigabit used by data centers or server applications. The client usually using 100 Mbps or 1 gigabit for the desktops and workstations, but servers, network cards, and the switches upgraded to 10 gigabit. Recently they introduced something called there was for the larger networks and the data centers there were 40 gig and 100 gig. But there is a catch in this case, because this 40 gig is physically 10 gig, which means 40 gig developed by bundling the 4 gigabit Ethernet, which is not providing serialization delay advantage. But this 100 gig later initially developed by bundling 10 hundreds, but later developed, which is not highlighted here, 425 gig, which is increasing the latency, reducing the latency. The new standard for the data center is not 10G. When we are purchasing the modern from the last year, I think everybody on the new data centers or the greenfield deployments, they are using 25 gig and compatible with 10, which means 10/25 switches and the network cards for the data centers. And these 5 gigabit Ethernet and 2.5 gigabit standards introduced for the home networking. Usually when you have a heavy user of gamer in terms of your home network, without increasing the band, home and enterprise networks are there. If you have cabling for the 1 gigabit Ethernet, now it is possible to run 5 gigabit Ethernet on the same cabling standard, which is on the Cat6, category 6 and category 5. These two are the new standards to run without changing the cabling on your system networks. These 5 gigabit Ethernet and 2.5 gigabit, now home networks are there with this Ethernet standard. For an example, this home routers are now equipped with 2.5 and 5 gigabit Ethernet ports. Your campus network can be run if it is previously wired with 1 gigabit. If you don't have budgets for the cabling upgrade, you can still use this new 2.5 gig switches and 5 gigabit Ethernet standardized network equipments with the same cabling without upgrade. And now we have 50 gig, 200 gig, 800 gig, and 1.6 will be coming soon. And these are the Ethernet roadmap if you are planning a network for next 5 years and something like that, and upgrading current network to a new one. So you can consider this Ethernet roadmap in terms of latency enhancement, latency reduction, as well as bandwidth enhancements. Okay, some of the slides, so we have 15 minutes. Some of the slides, these slides from here are mostly end-to-end latency enhancements. I will tell you some of them we are not testing, but I will give you an understanding for your network planning and troubleshooting on the modern network. I can give you certain explanations on the latency reduction. So another way of doing another comparison is application to application end-to-end latency. In the first left side diagram, you can see that if you purchase usual cable, usual server, and general enterprise server, enterprise operating system, and enterprise normal store and forward switch, which the normal costing, you get the best bandwidth somewhere around 70 microseconds end to end from your server to server one-way latency, because server adding usually the kernel stack and which is TCP/IP stack adding with the network drivers and the network card then in 25 microseconds. That normal switches which are not cut through, store and forward switches usually adding 20 microseconds, and again remote server will be adding another 25. So even with one switch connected to two machines, it's taking one-way delay for your applications 70 microseconds. This can be improved. This is more than 10 years back, I think. This can be improved up to the level of 11 microseconds. Now we can do somewhere around 5 microseconds with the further optimizations. So there are further possibilities to optimize and tune the servers, even changing server BIOS, operating system tuning, and the network card driver selections. The usual network cards taking more latency than smart NICs. Usual network card just forwarding the traffic with those are cheap as less than $200, but smart NICs costing more than I think $1,000. So those are there are low latency smart NICs. You can get these numbers by using smart NICs and further tuning of your operating systems with the low latency, and the tuning the server BIOS, and selecting the cut-through switches, which is called in Nexus 5000 in this case. Port-to-post latency is 3.2 microsecond, but there are now sub-microsecond level switches such as less than 500 nanoseconds one way, and this is quite possible. You can get even 5 microseconds or less than 5 microseconds, sometimes 3 microseconds latency with the modern tuning and selection of devices for your data centers. All right, this is the switch selection. If you are selecting store and forward, usually the process is it's taking time into last in first out, and the bottom is first in first out. The bottom one representing the cut-through switching, which means you don't need to get your entire packet into the switch, and the cut-through switches require entire packet gets into the switch and then send it. So the usually if somebody asks question on what's the difference between store and forward and cut-through switching. Cut-through switching just reading the first packets, first few headers of the packet and forwarding it to the destination port or next port. And but for the store and forward, you need to get entire, including the headers, so entire packet into the switch buffers and then forwarding. You can't get certain features by even though cut-through switching is faster. Store and forward has the possibility of implementing certain security measures by checking entire packet integrity and all. But it is impossible with the cut-through switching because we are just forwarding, considering the latency and reading the first few headers of the packet. So there are advantages and disadvantages, but if you need low latency data center environment, you need to consider cut-through switches rather than selecting store and forward, which is adding the more latency, which is somewhat comparable in this normal switch adding 20 microsecond port-to-port latency, but the cut-through switches are sub-microseconds these days. Few microseconds can be reduced by selecting cut-through switch. And these are not tested in your final examinations because these are mostly kernel additional knowledge for your latency tuning additional knowledge. The OS kernel bypass is possible because, as I initially mentioned on the latency breakdown, there is something called protocol delay. The TCP/IP and the kernel adding more latency, the huge latency for the low latency applications. There are smart NICs, like in this case, the solar flare, which is from AND SmartNICs, possible with more than $1,000, and implement something called kernel bypass user space tool, which in this case called Open Download, which is again open source component. And it can be communicate. Your application can directly communicate with your network card rather than going through the kernel, which is named as kernel bypass. So TCP/IP protocol overhead will not be impacted here, and tremendous latency reductions are possible by using this kernel bypass methods. So then there is something called modern day AI workloads, heavily dependent on some protocol named RDMA, Remote Direct Memory Access, which means the remote direct memory access usually supported by protocol named InfiniBand, which is different from Ethernet. It is a protocol defined only for mainly targeting the scientific applications and ultra low latency, and the nowadays using AI and machine learning applications. So you can implement this RDMA protocol to offload RDMA protocol, which is quite interesting, which is contrasting to TCP/IP stack, and you can implement by using the supported network cards, which is RDMA supported, and now it's supporting Ethernet on top of Ethernet as well. Now, initially it supported only the low latency protocol named InfiniBand, which doesn't have any Ethernet layers, but later Ethernet supported. And what is the function of is the RDMA is pushing the protocol functionalities not running on the operating system. It's running everything on the IO adapter, which is the SmartNIC, which means it's quite faster and operating system overhead pushed to the network interface card. These cards are powerful with they're having processors as well. Those are called SmartNICs, not normal NICs. Network interface cards with smart capabilities like smartphone and dumb phone. So these are smart NICs, and you RDMA protocol built to offload the traffic offload engine, which is TCP, or the protocol overhead will be pushing to the IO adapter, which is the smart NIC, and several buffers. Buffers reducing, I mentioned you that buffers increasing the latency, which is the queue delay. So queue delay reduced by offloading, entirely removing some of the buffers or pushing the buffers to adapter network card, which is hardware based, not software based. And application buffers can directly talk to the hardware based adapter buffer, and all the functionalities of application, the protocols, network protocols pushed to the SmartNIC by using something RDMA. IOOP is a protocol use case defined by IBM, which is adapted by RDMA protocol development. In this case, all the buffers removed from operating system, all the TCP/IP and all the protocols, application network protocols removed from the network stack, which is operating system, and push into the by design it is pushing into the network interface card. So this architecture providing with RDMA, you can see the without RDMA and with RDMA diagram comparison, most of the buffers push to the adapter, and the protocol push to the network stack push to the software from operating system to the network interface card. application buffers can directly talk to the network card rather than going through the operating system. So operating system overhead and the traditional protocol overhead avoided, and directly application has the capability to talk to the network card. So this is the latency reduction we are seeing on the modern data centers. Okay, let me go ahead and explain further. There are other things as well. Traditional CPU architecture having an issue because the CPUs are defined previously some time back by a person, the scientist named von Neumann. So modern day, current day CPU architecture, we are mostly developed our modern CPU architectures by using this von Neumann architecture. Occasionally, the FPGA and non-von Neumann based deployments are there, but most of the computers are still based on von Neumann architecture. This von Neumann architecture has several suboptimalities. If you send packet through the NIC interface, it is copying multiple. It is initially the first step. It is copying to the CPU registers, then it is going back to the application memory, and there is another copy going through the IO memory pool, another one copying from the IO memory pool to the application memory. So it is not optimized for the latency for this von Neumann architecture. Now this kernel bypass mechanisms, and there is something called zero copy architecture. It is just copying directly to the application memory rather than going copying here and there with the multiple registers and application memories or IO memory pools. So that's called kernel bypass with zero copy internally. So this is to avoid, the zero copy is to avoid von Neumann architecture bottlenecks for the latency. So these are the host side, host-based networking improvement possible on the modern data centers to reduce the entire end-to-end latency. I added few slides for your reference, but I'm not going through this and tested on your assignments or the final examinations. This is about the alternative protocol for the high performance computing and ultra low latency network. The software consortium is Open Fabrics, and the hardware standardization consortium is IBTA. And this is the packet structure of IBTA for the InfiniBand. And this is the roadmap as we see on the Ethernet roadmap. They have similar bandwidth, and you can check the latest one by the web. These are somewhat earlier. They are even targeting 1.6 gig and 3.2 gigs, similar to Ethernet. The Ethernet was lagging, recently pick up with the competition of InfiniBand. And these are the latency comparison between RDMA 10 gig, 1 gig. You can clearly see the red, which is the lowest latency. We are in microseconds, and the other options are high latency. And this is the software stack. And the last two slides, these are now you can implement the InfiniBand technologies on top of Ethernet. The first there is something called Rocky, which is available on the most of the network card, as well as the switches are now supporting. You can implement RDMA or converge Ethernet on your data center servers with these network cards and switches. Similar to, you can get the similar performance with on top related to InfiniBand by implementing the protocol named RDMA over converge Ethernet. So RDMA can be implemented on Ethernet. The first variant is Rocky 1. The short form of RDMA or converged Ethernet is Rocky 1. It's replaced with the only Ethernet layer. Now the Rocky version 2 has IP and UDP support with the TCP stack. So it is basically useful in terms of ultra low latency deployment in terms of protocol level, because Ethernet and TCP/IP are suboptimal standards developed more than 5 decades back, and those are not optimized for any use of low latency. Now these protocols are possible to implement in terms of modern data centers with the ultra low latency tuning and applications. And these are the packet structures between Rocky version 1 and version 2. So basically, just I wanted to highlight that how far we can go by the tuning of one metric, which is the latency. Similarly, you can do it for other matrices by doing enough research. It is quite important to understand and ready for the modern workloads and data center networks by using these modern technologies. So these are the reference book I included. Probably you can find it through the web, or some of them are in the library. These are quite useful if you want to prepare for the real world networking and the troubleshooting stuff with the modern developments. So that's all for the day. Any questions in terms of any of these things? Probably you can ask today or the next week, and you can email me as well. Okay, that's all for today. Let's meet on, I think next class will be on 18th, which is after the New Year, April New Year holidays. And I will be uploading an assignment of after the assignment and these slides on the next week. Probably you can start your first assignment, and I will provide submission date longer than usual due to considering holidays, and as well as I can provide you additional 2 weeks for this thing, what's called the assignment one. Okay, thank you very much. Thanks for participating today. And if you have any question, you can reach me. Thank you.
Thank you, sir.
Thank you.
Thank you very much.
Bye. Welcome.